okay? So ultimately, we're working up to kind of two things we care about in linear algebra in the context of this class: eigenvalue problems and the solution of linear systems of equations, particularly on a computer. So, and again, you know, this is sort of very, very simple, but we got to start here. So those of you that know some of this, you might be bored, but understand we're working up to eigenvalue problems. So if I have a vector C, we normally write this in vector notation, vector C, a matrix A, and a vector B. I want to do a matrix vector dot product, essentially. The way I compute the components of C, and I like to remember it like this. I like to just say it in words. So C1, the first component of C, is the first row of A dot product B, right? The second component of C is the second row of A dot product B. You all know what a dot product is. And finally, the third component of C is the third row of A dot product B. And so there's what it is written out for each component. Everybody okay? Matrix vector dot product. So I figured you probably know that. So in words, the Ci, right? So I being the ith component of the C vector. The Ci is the dot product of the ith row of A with B. So you probably all know that, but what you may not know is how to do matrix multiplication. So in matrix multiplication, again, I like to use words. So the C11 component of C, right? So then now we have three matrices, right? So this is a matrix C, a matrix A, and a matrix B. So the C11 component is the first row of A dot product first column of B. The C12 is the first row of A, second column of B. Right? C13 is the first row of A, third column of B. And these go on like that. So essentially, you can look at the lowercase indices and tell, this is associated with the row of A, and the first one is the row of A, and the second one is the column of B. Right? So for example, to jump out of order, the C32 is going to be the third row of A with the second column of B. Right? Dot product. So there's a couple examples written out, dot products, in words. The Ij, where Ij is the component of the C matrix, the Cij is the dot product of the ith row of A with the jth column of B. So, well, I was going to work that out, but there's the answer. I meant to hold off on that. Yeah, so again, we take the first row here, 2, 1, take the dot product with 1, 2, right? So that's going to be 2 times 1, which is 2, plus 1 times 2, which is 4. Right? Same thing, 3 times 1, which is 3, plus 2 times 2, which is 4. 4 plus 3 is 7. So we'll go ahead and look at a matrix. If we have a matrix 2, 1, 3, 2, we multiply another matrix 1, 3, 1, 2. And I'm just going to write it out very explicitly here. Go slow. So our result will also be a matrix. I put the little dashed lines in there to just separate the locations, the entries in the matrix, right? So we have, for the 1, 1 entry, we have the first row of A, right? If this is A, this is B. We have the first row of A with the first column of B, right? So that's 2 times 1 plus 1 times 1, right? And then for the 1, 2, we have the first row of A times the second column of B. So that's 2 times 3 plus 1 times 2. And then we continue, right? 3, 1 plus 2, 1, 3. Plus 2, 2. And so then if we just work out the math, you get 3, 8, 5, 13. So that's the second example. So another useful thing in linear algebra is to take the determinant of a matrix. So who knows the formula for a determinant of a matrix? 80 minus BC, right? So you can memorize that formula if you want. 80 minus BC. I like to just kind of think of it graphically, right? So I just make an X, right? So it's AD minus BC. That's how I remember it. Just make an X. And the reason that helps me is because when you go to bigger matrices, you can sort of also do it graphically. So for a 3 by 3 matrix, I mean, you can memorize the formula if you want. There it is. I think it would be pretty hard for me to memorize that. But what I do is, again, just I start with A. Start with A, and then I cross out the row and column, and then I take the determinant of what's left over. Just use X. Right? EI minus FH. Right? So that's that formula. Okay. And then the thing you do have to remember is there's a minus sign, so they'll always alternate plus, minus, plus, minus, plus, minus. And this generalizes to very large matrices. So then for the second one then, I'm going to take B, I'm going to cross out the row and column, and then take the determinant of what's left. Right? So D times I minus F times H, that's what you have there. For C, I'm going to cross out the row and column and take the determinants of what's left. D times H minus E times G. So then all you have to remember is just that it's going to go plus, minus, plus, minus, plus, minus. And that generalizes if I had a bigger matrix, like if I had a 4 by 4, I wouldn't recommend ever taking the determinant of anything bigger than a 3 by 3 by hand. Use the computer, but you could do the same thing, right? So for a 4 by 4, you're going to take this guy times, you cross the row and column out, and then figure out what the determinant of that guy is, right? Well, the determinant of that guy, then you do this again, right? and then you'd go same thing, right? Now you'd have a minus sign, and then compute the determinant of that 3 by 3. Then you'd have a plus sign and compute the determinant of that 3 by 3. And this goes on and on. Again, I would never take the determinant of anything bigger than a 3 by 3 by hand. Use a computer. The computer doesn't actually implement this rule like I showed. There's a better way to do it in a computer. So one thing that's useful, or what can we use determinants for? When we solve linear systems of equations, we often solve a system of equation that has the form, we're looking for the solution x for a matrix A times a vector x equal to a vector B. Ax equal to B. This is what we're, if you've taken, well, I guess only a couple of you took Res 3 from me, but so far, but if you take Res 3, I mean, this is all we do all class. Solve big matrix equations of this form. And so we're looking for x in this way. And so the way you do this is you multiply, and it matters when you're doing matrices. Like, so if you're multiplying scalars, it doesn't matter if you multiply on the left side of or the right side of an equation. Right? So if I just multiply that equation by 2, I could say 2ax, or I could say ax2. Right? Doesn't matter. But with matrices, it does matter on which side of the equation you multiply. But if I multiply then both sides of the equation by A inverse, right? Any matrix times its inverse is the identity matrix. And the identity matrix times any vector is just the vector. So that's the solution to that equation. It's just the thing is, A inverse is not guaranteed to exist. Just because a matrix exists, it doesn't mean its inverse will. And one way we can quickly determine, so if a matrix inverse does not exist, it's said to be singular. And one way we can quickly determine if a matrix is going to be singular before we attempt to take the inverse, which is an expensive operation in a computer, is to compute the determinant. If the determinant is what, the matrix is singular. Anybody know? If the determinant equals 0, so a matrix is singular if its determinant is 0. So in other words, if the determinant of a matrix is 0, it doesn't have an inverse, and therefore this system of equations doesn't have a solution. Okay? I think that's a good place to stop for today. So we're continuing our discussion of linear algebra, again, because we're going to use this extensively in the class to solve for principal stresses, to do matrix multiplication, other things like that. One of the most used, I guess, useful parts of linear algebra is in solving linear systems of equations. And so if we have a system of equations that we'd write in matrix form like this, we have a matrix. This would be A. This is a vector x. This is a vector B. We consider that we know all the components of A and we know all the components of B, and we're seeking the solution to x, right? So this is no different than if we just wrote down the system of equations. So in other words, if we did our matrix vector multiplication on the left side, remember we talked about last time, so we'd have an equation A11 x1 plus A12 x2 plus A13 x3 is equal to B1, A21 x1, A22 x2, A23 x3 is equal to B2, and likewise for the last equation. Right? So when we solve matrices, solve systems of equations in this form, in the actual matrix form, we can work through some things we call matrix row operations to do it for us and to solve these system of equations. And they really just break down to kind of 3 rules. And the reason that it's nice to have these 3 simple rules is because we can implement those 3 simple rules into a computer easily. And in fact, whenever you have any direct solver that solves a linear system of equations in a computer, they just implement essentially these 3 rules. Right? And so the first one is that swapping rows doesn't change the solution. Right? And that should be obvious because, and that's part of the reason I wrote out the first 2 equations, right? If this is just sort of a convenient way to write that, and we were going to work out the solution to that linear system of equations by hand, of course it doesn't matter if I simply write the second equation on top of the first one, which is essentially all I'm saying when I say that swapping rows of the matrix in solution vector don't matter, right? Because it wouldn't matter if I just simply wrote one of those equations before the other one. Adding rows together doesn't change the solution. So we often do this, like if you know, these are things you've been doing since Algebra 2, at least, right? Or I guess Algebra, since high school, right? When you go to solve a system of equations, often you can just add the 2 equations together because that will conveniently eliminate one of the terms, right? And so we do this all the time. Multiplying a row by a scalar doesn't change the solution, right? We all know this. If you have an equation and you multiply both sides of the equation by a number, it's still the same equation. It doesn't change the solution. So we can solve linear systems of equations using some combination of these 3 rules. Right? And again, the reason it's nice to break it down is because this is the 3 rules we essentially implement into a computer in a logical way, and we let the computer solve it for us. However, it's useful to do this at least once or twice by hand because it gives us a convenient sort of set of tools for solving for something called eigenvectors, which we'll learn about soon. The next topic, actually. So let's look at an example. So this is our system of equations written like this. And what we want to do is solve for x1, x2, and x3 using these 3 rules. Right? We call these row operations. So I'm going to write the system of equations like this. So there's our A matrix. And I'm just going to put a dashed line here. And then I'm going to write the solution vector there. So 6 minus 6, 3. So again, that's our system of equations, and I've just rewritten it like that. Okay? Now, what my goal is to perform those row operations one by one, and it doesn't matter what order we do them, but I want to perform those row operations such that the left-hand side, the side on the left of that dashed line I drew, becomes the identity matrix. So I just want a 1, 1, 1 over there on the left-hand side. Okay? So the first thing, and you know, as you practice this, you can, while it doesn't matter what order you do them in, a clever choice of the order can reduce the amount of work you have to do, right? So automatically, just looking at that, I can see that if I swap the third row and the first, then I have a 1 on the diagonal of the first row, right? And so this is going to be a little slow, I mean, especially for those of you that have seen this, but I just want to be very explicit. And I'm not going to make you do this 1,000 times in this class, but let's look at it slowly one time, right? So what we're going to do is we're going to swap row 1 with row 3. write out the results. So 1, 0, 2. We'll leave the next row alone, 0, 0, 3, minus 6. 2, 3, minus 2, 6. Okay? Now, I'm going to multiply the second row by a constant, right, by a number. And I'm going to choose that number carefully so that I can turn that 3, it's 0, 0, 3. I want to turn that 3 into a 1. Right? So what would I multiply by? A third, right? So I'm going to multiply 1/3 times row 2, leaving everything else alone. And of course, as you get better at this, you can sort of do multiple operations at once. I'm not doing that here. Again, I'm going very slowly, so you can see what I'm doing. Right, so I just, I could have said I divide by 3, right? But I want to, dividing by 3 is the same as our rule was multiply by a number, right? So we want to multiply by 1/3. That keeps our rule simple, right? Okay. Now if I swap the second and third row, then I have a 1 where I need it to be, right? So swap row 2 and 3. Leaving everything else alone. All right. Okay, so now I will use kind of 2 rules in once. What I want to do is I want to eliminate that 2 in the second row, right? So what I'm going to do is I'm going to multiply the first row by minus 2, right? And then add it to the second row. Multiply the first row by minus 2, add it to the second row. So I'm going to say minus 2 times row 1 plus row 2. And that's going to give me everybody see what I did there? Right, so minus 2 times 1 is minus 2, plus 2 is 0. Then I have minus 2 times 0 plus 3 is 3. Right? Minus 2 times 2 is minus 4, plus minus 2 is minus 6. Right? Minus 2 times 3 is minus 6, plus 6 is 0. So that's how I went from there to there. Okay? Now, if I divide this row by 3, or multiply by 1/3 again, I'll have a 1 right there. So 1/3 row 2, 1, 0. There. So this is almost always what I do is when I do these, I try to make this left, the thing left of the diagonal line, then I stop drawing the horizontal, the vertical line, then I stop drawing there. Everything to the left of this, I want to make this guy upper triangular, right? So that it has zeros down below. One's on the diagonal, and then it becomes real easy to eliminate above it. And by the way, I mean, we're working on a 3 by 3, but this works for a 1,000 by 1,000 matrix. This is exactly what a computer does to solve big matrices. So then, so then I can just eliminate above. So 2 times row 3 plus row 2. 2 times row 3 plus row 2. Yeah. No. 2 times this row would give me a 2 there, and then I'm going to add it to that. 2 plus minus 2. Yeah. So. Yeah. So here I have 2 times 2 is minus 4 plus 0 minus 4. And then, now on this last one, minus 2 times row 3 plus row 1. So now, minus 2 times row 3 plus row 1 gives me 1, 0, 0, 7, 0, 1, 0, minus 4. All right. So what's left on the right-hand side there is the solution. So my solution vector is x is equal to 7 minus 4 minus 2. So in other words, x1 is equal to 7, x2 is equal to minus 4, x3 is equal to minus 2. A is equal to 2, 3, minus 2, 0, 0, 3, 1, 0, 2. B is equal to 6, minus 6, 3. Linear solve A, B. 7 minus 4 minus 2. 7 minus 4 minus 2. Any of y'all ever use Mathematica? You ever use Wolfram Alpha? Right. So Mathematica is the engine, the compute engine behind Wolfram Alpha. So Wolfram Alpha came out in like 2009 or something, but Mathematica has been developed since 1984. It was originally written by Stephen Wolfram, who might possibly be the smartest man alive, literally. He's still alive. I think he wrote his first scientific paper when he was 14, and he got his PhD from Caltech when he was 21. So anyway, Mathematica. I'll use it a lot for quick checks and calculations in the class.